Hey guys, welcome to Safi Next. In continuation to my previous video on binomial distribution, in this video I will prove two very important properties of binomial distribution, namely the average and variance of binomial distribution. You can refresh the concept of variance for clear understanding of this lecture by watching my video on the concept of variance. So I will prove that the two quantities are respectively given by these two relations. That is, the average is given by capital N times P and the variance is given by capital N times P multiplied with 1 minus P. In this equation, capital N is the total number of trials and P is the probability of occurrence of one of the two possible events in a single trial. If you recall from my videos on binomial distribution, the relation for probability in binomial distribution is given by P of n equals n to n P raised to the power n and Q raised to the power n minus n, that is capital N minus small n, where Q equals 1 minus P and represent the probability of the second event in a single trial. With the help of equation 3, the average can be written as n bar equals sum running from small n equal to 0 to capital n times P of n. Substituting the value from equation 2, we can straight away write the average of small n into this form, or writing the small n to the other side of the brackets, I can write it into this form. Now, considering the parameters P and Q, two independent variables, equation 5 can be put into another useful form by considering this identity, that is P times partial over partial P and the whole applied to the probability of binomial distribution, that is summation from n is equal to 0 to capital N to n P power small n Q power capital N minus n, and that can be written equal to P taking the differential to inside the summation, and taking differential inside the summation, I can rewrite that whole expression into this form. Since we are considering Q independent of P, therefore applying the operator partial over partial P to the term P, I can write that as NPN, and the whole relation can be put into this form, and taking the P and taking the leftmost P to combine that with P power n minus 1, I can rewrite that as NPN, and the whole relation takes this form, that is summation from n is equal to 0 to capital N to n the whole multiplied with n times P power small n Q powers n minus n. Now, using the left side in equation 6 for the right side in equation 5, we obtain the average value of n equals P times the derivative with respect to P, the whole applied to summation n is equal to 0 to capital N P power n Q power n minus n. But from binomial theorem, we know that the quantity inside the bracket of equation 7 is also equal to P plus Q raised to the power n, as given in equation 8. So using equation 8 in equation 7, we can write the average value of n in the form n bar equals p times derivative with respect to p of p plus q the whole raised to the power n. And applying the operator, we can rewrite that as p times capital N the whole multiplied with p plus q raised to the power capital N minus 1. Now note that the link established in equation 6 is valid for any choice of p in q. However, if we set q equals 1 minus p or p plus q equal 1 in equation 9, then equation 9 straightaway reduces to n bar equals p times capital N. Equation 10 is one of the two required results. Equation 10 is in fact equation 1. Now let us prove equation 2. To this end, I begin from the definition of variance, which in terms of binomial distribution can be expressed as summation from n is equal to 0 to capital N p of n the whole multiplied with n minus n bar the whole squared. Now note carefully that the average of n, that is n bar in this equation, is a number and the summation does not apply to it. This is important to note. With this fact in mind, we can put this relation into another form by opening the square. That is, I can write sigma square equals summation from n equals 0 to capital N p of n square plus n bar square minus 2 times n bar. Now opening the bracket and counting individual term, I can multiply summation n is equal to 0 to n pn with each term and can write the equation finally into this form. And if we look into this equation very carefully, the first term is in fact the average of n square. In the second term, I have factored n squared to the left of the equation, and inside the bracket is the sum over all the probabilities, which is obviously equal to 1. And in the last term, I have again factored 2 times n out of the summation and have written the terms and have applied the summation over the product of probabilities Pn and n. So the second term is just n bar square. I'm writing that n bar square because the what is inside the bracket is 1, and the third term is 2 times n bar times the probability of the average value of n, which is again n bar, and n bar times n bar is equal to n bar squared. So I can finally write the equation by combining the last two terms, that is n bar square minus 2 n bar square, which is equal to minus n bar square. In the final result, I can put into the form the average of n square minus the square of the average n. Is another very useful form of variance. Now let us find the average of n square, that is n square bar in equation 11. That is the first term at the right. So I can write the term again into its original form. That is, I write the average of n square equals summation from n is equal to 0 to capital N p of n multiplied with n squared. And if I substitute the value of Pn, I can rewrite the equation into that form where I have just substituted the value of p of n. Now, like I did in equation 6, one can easily prove that the right side of equation 12 can be expressed as this one equation, that is summation from n equal to 0 to capital N into n square p raised to the power small n q raised to the power capital N minus 1 equals p times the derivative with respect to p, again p and then the derivative of p, and then the relation for p of n, that is summation n is equal to 0 to n to n, p raised to the power small n, q raised to the power capital N minus 1. And again, writing the probability in terms of p plus q raised to the power capital N and applying the derivatives with respect to p at its own number, I can carry the calculation as in these two steps and can write the final equation into this one form. And substituting this value back into equation 12, I can write equation 12 again into this lengthy form. Now squaring equation 10, I can write n bar square equals capital N squared p squared, putting values from equation 14 and equation 15 into equation 11, we can rewrite the variance sigma square into this one form. Again, it's a lengthy relation, just have a look on it. We have substituted the values from those two equations. And using the condition that p plus q equals 1, it can straight away be reduced to sigma square equals n times p squared the whole multiplied with n minus 1 plus np minus n squared p squared. And further simplifying this relation, we can put it into the form of equation 17, that is sigma square equal to n times p times 1 minus p. You see, equation 17 is in fact the proof to equation 2 that I showed you in the beginning of this lecture. So equation 17 is the simplified form of the variance of binomial distribution.